Okay, you've handed us a stack of sources, and wow, it's a truly fascinating collection. It looks like we're starting with a very specific puzzle in theoretical physics
Hmm.
and ending up asking some of the biggest questions imaginable about reality, consciousness, maybe even ourselves.
That's the plan. It's quite the intellectual journey you've mapped out.
So our mission today, as always in the deep dive, is to really plunge into this material you've shared. We want to pull out the most important bits, find those aha moments, make these complex ideas click.
And try to make sense of it all together. We're starting with what seems like a fairly contained thought experiment, right? Rooted in classical physics.
Exactly. Norton's dome. That's our starting point. It's this clever thought experiment in classical mechanics.
Designed specifically, as I understand it, to push the boundaries of what we think we know about cause and effect, prediction, especially in Newton's world.
Right, that deterministic view. And this dome seems to challenge that directly.
Yeah, it takes aim at that long-held belief that the future is completely locked in, dictated down to the last detail by the past.
So we'll really unpack what this dome is, the paradox it throws up, why it seems to break the rules we usually take for granted in classical mechanics.
And how physicists and philosophers have kind of picked it apart, criticized it.
Definitely. Then, because you raised some really brilliant, insightful questions in these sources, we'll dig into how this puzzle compares to other physics concepts. You mentioned Lagrange points.
Points of equilibrium and gravity. It's an interesting comparison.
And ultimately, we're going to follow these threads. From this classical physics paradox, all the way to these huge questions: free will, quantum mechanics and thinking, consciousness.
And even stretching into speculative ideas about what the very dimensions of reality itself.
Pretty much. So yeah, potentially going from a frictionless surface to the fundamental fabric of the universe and our place in it.
It promises to be a wild ride.
Yeah.
Expansive, for sure.
Absolutely. Through some surprising and pretty profound corners of physics and philosophy. So let's just dive right in. Okay, section 1 then. Norton's dome, unpacking the paradox. Let's start right at the beginning. What is this thing? Norton's dome. Who came up with it? Why?
Right. So Norton's dome is actually relatively modern as far as these classical thought experiments go. It was proposed by a philosopher of physics, David W. Norton, back in 1996.
Okay, so fairly recent.
Yeah. And his core purpose, the reason he constructed this theoretical setup, wasn't really to describe something you could actually build. It was specifically designed to explore the limits of determinism.
The limits within Newtonian physics itself.
Exactly, within that well-established framework.
Yeah.
It directly challenges a really fundamental assumption that's, well, it's core to classical mechanics.
Which assumption is that?
The assumption that if you know the precise initial conditions of a system, like its exact position and its exact velocity at one specific moment, then you can uniquely figure out its entire future motion and predict everything that happens next.
Okay, so it's deliberately built to poke at a potential weakness, maybe an edge case, in our classical understanding of cause and effect. So how is it set up? What does this theoretical dome actually look like? What are its features?
Well, like a lot of these thought experiments in physics, it relies on some idealizations. Big ones.
Like assuming no friction.
Exactly. First off, it's a perfectly frictionless surface.
Yeah.
That's pretty standard in these kinds of classical mechanics problems. Helps simplify things, lets you focus on the core dynamics. But it's important to remember it is an idealization.
Okay. Frictionless. What else?
The absolutely crucial feature, though, is its shape. Its geometry. It has this very unusual shape. It's not just a simple hemisphere or, a parabolic curve.
Unusual how?
This shape is precisely defined by a very specific mathematical formula for its potential energy function.
Ah, okay. And your sources give that function. It's HR r to the power of 4 divided by 2g. H equals rz fourth over 2g.
Yeah.
Can you break that down? What do H, R, and G mean here?
Sure. So H is the height of the dome at any given point on its surface.
Okay.
R is the radial distance measured horizontally outwards from the very top point, the apex, the peak of the dome.
Got it. Distance from the center peak.
And G is just the standard acceleration due to gravity, the thing pulling stuff downwards.
Right. So why is that specific R4 term so important? Why that particular power?
That R4 term is what gives the dome its really peculiar, mathematically specific curvature right at the very tip, at the apex where arc is 0. This isn't a shape you'd find in nature. It's not something that just happens when gravity acts on normal materials.
It's purely cooked up in the math.
Exactly. It's a mathematically defined shape, chosen because of the strange properties it introduces into the equations that describe how something moves on it.
Okay. Got it. So we have this weirdly shaped, theoretical, frictionless dome defined by this r to the fourth math. What's the actual experiment supposed to be? What do we do with this dome?
The thought experiment involves taking a particle, you imagine it like a tiny, perfectly smooth point mass or a tiny ball, and placing it perfectly at rest right at the very top of the dome, at the apex.
So initial condition, particle at 0, 0, the peak, and its velocity is 0 relative to the dome's surface at time t0.
Precisely. That's the critical initial setup.
Okay, now, just for comparison, what would normally happen in classical physics if you placed a similar perfect ball perfectly at rest on the very top of a smooth, regular dome, like a perfect sphere?
Right. On a typical smooth dome with a standard curvature, like a sphere, if you place the ball exactly at the peak and it's perfectly at rest, and you assume no friction, no air currents, no vibrations, nothing.
Ideal conditions.
Yeah, under those ideal conditions, the net forces on the ball would be perfectly balanced. Gravity pulls it straight down, the normal force in the dome pushes it straight up, they cancel out, the net force is 0.
So it should just stay there.
It should just stay right there at the peak, forever, perfectly motionless. That's the stable equilibrium point in that standard scenario.
It's okay. That makes intuitive sense for a regular dome. So why is Norton's dome different? Where does the paradox actually kick in?
This is where that specific unusual curvature, defined by the R4 function right at the apex, becomes critical. The shape at the very peak of Norton's dome is mathematically designed so that a particle placed perfectly at rest there also experiences 0 net force initially.
Just like the regular dome, the forces balance at that exact point.
Yes, at that single point, RO0, the force is balance, gravity down, normal force up, net force is 0. However, the way the force changes as the particle moves just an infinitesimal distance away from that center point is where things get weird. And that weirdness comes directly from that specific R4 mathematical form of the potential energy near the apex.
Okay, 0 net force initially still seems like it should stay put. How does the paradox actually emerge from that?
It emerges when you rigorously apply Newton's second law, ESMA, to a particle moving on this specific surface. When you do the math, when you analyze the motion of a particle on a surface defined by that R42G potential, you end up with a particular differential equation that describes the particle's motion in the radial direction, r, relative to the apex.
And the source material gives that equation. It looks quite simple. E2r dt2 equals gr. Second derivative of position equals g times position.
It does look deceptively simple, doesn't it? Almost like something you'd see for, say, simple harmonic motion. But it's not. It's the mathematical properties of this specific equation, especially when combined with those precise initial conditions at rest at the apex, so RE0 and velocity GSEO is 0 at time t0, that cause the trouble.
Trouble how?
The absolutely crucial point, the mathematical result that Norton demonstrated, is that this particular differential equation under these specific initial conditions is shown to have non-unique solutions.
Non-unique solution. Wait, for the exact same starting point, the same initial conditions.
Yeah.
But isn't that like the fundamental rule of classical physics? Same start, same future.
Exactly. That is the core of the paradox Norton's dome presents. It hits right at that fundamental assumption. Non-unique solutions here mean that from the exact same initial state particle starting perfectly at rest at the apex, R00 Doro dz0 at t deloro, the standard deterministic laws of motion governing this specific surface, as described by Newton's laws in this equation, do not give you a single unique prediction for what happens next.
Wow. Okay. So if the math allows for multiple futures, what are they? What are the possible paths for this particle according to the equations?
Well, there are multiple mathematically valid solutions that satisfy both the equation of motion, d2 par dt2 to weeks gr, and those initial conditions, r0, d0, dt0 at t0. One possible future is the one that feels intuitive. The particle just remains stationary at the apex indefinitely.
Stays put. Okay, that makes sense. Forces are balanced there. Staying put is a valid solution.
Right. R to t for all time t is a perfectly good solution to the equation with those initial conditions.
So what's the other possibility? The one that breaks our intuition?
The other set of solutions is what generates the paradox. The mathematics also allows for solutions where the particle, after sitting at the apex for some period of time, spontaneously begins moving downward along the dome, away from the apex. R starts increasing.
Spontaneously, like just decides to roll.
That's how it appears from the math. And here's the really bizarre part, the part that truly challenges determinism. According to the mathematics, the particle can start moving downward at any arbitrary time after it was placed there at t0.
Any time, like 1 second later, 10 minutes later, next Tuesday.
Any positive time t you could imagine. The math allows for a solution where the particle stays at RO0 from t0 up until some arbitrary time t0, and then starts moving according to a specific trajectory away from the apex. So it could sit there for exactly 1 second, then move. Or sit there for exactly pi seconds, then move. Or 106 seconds, then move. Any positive start time t is mathematically permissible.
And there's nothing in the model that causes it to pick one specific time t over another. No external nudge, no vibration, no quantum jiggle.
That's precisely the point within the mathematical model. There is absolutely no external force or trigger defined or included in the model that causes this spontaneous motion to begin. There's nothing that selects why it should start moving at, say, t5 seconds instead of t15 seconds, or instead of just staying put forever. This spontaneous motion at an arbitrary time arises purely from the specific, peculiar mathematical structure of the equations governing motion on this uniquely shaped dome, given those exact initial conditions.
And that is the paradox laid bare. Identical, perfectly specified starting conditions seem to lead, mathematically at least, to multiple possible, equally valid future histories, purely within the framework of classical mechanics.
Yes.
That undeniably challenges that traditional, strict, almost clockwork view of classical determinism we often associate with someone like Laplace.
It certainly forces us to scrutinize the assumptions embedded in our classical models and question whether the mathematical structures we rely on always guarantee the unique outcomes we intuitively expect, especially in these highly theoretical, perhaps pathological scenarios.
Okay, that explanation of the paradox itself is crystal clear. It's a theoretical setup, a mathematical construct, designed specifically to highlight a potential loophole or edge case in classical determinism. Let's move on then to section 2 and start analyzing the implications and, importantly, the critiques of this whole thought experiment. What does this paradox really mean philosophically, and what do the critics say? Why might it not be as world-shattering as it first sounds?
Right. The most immediate and significant philosophical implication, as we sort of touched on, is the direct challenge it poses to what's often called Laplacian determinism.
Named after Pierre-Simon Laplace, the 18th century mathematician.
Exactly. His famous idea, or perhaps thought experiment in itself, was this concept of an all-knowing intelligence, often nicknamed Laplace's demon.
The demon that, if it knew the exact position and momentum of every single particle in the universe at one instant,
it could, using Newton's laws, calculate the entire future history of the universe and also perfectly reconstruct its entire past. It painted this picture of the universe as a giant, deterministic clockwork machine.
A universe with absolutely no surprises, no real branching possibilities. Everything that happens had to happen exactly that way, given the initial state.
Precisely. Norton's dome, then, offers a counterexample, albeit a highly theoretical one. It suggests that classical mechanics, the very foundation of Laplace's vision, may not actually be fully deterministic in all conceivable scenarios. Specifically, it fails in this strange, idealized edge case.
So it highlights that the assumption that initial conditions always lead to a unique future state, which is absolutely central to classical determinism, might have theoretical limits. Limits found even within the mathematical framework of classical physics itself.
Exactly. Under very specific and, importantly, unusual conditions. It's not suggesting that Newton's laws suddenly stop working for planets orbiting the sun or for calculating the trajectory of a baseball.
Right. It works fine for everyday stuff.
But it's asking, does the mathematical structure of classical physics always guarantee unique outcomes in every possible scenario you could construct mathematically, including highly abstract and artificial ones like this dome?
Okay, so it's like finding a tiny, almost invisible theoretical crack in the seemingly solid bedrock of strict classical determinism. But as you mentioned, the critics jump on this, right? They argue that the paradox only arises because the setup is so theoretical, so idealized, so, well, unphysical.
Absolutely. That's the primary and most common critique of Norton's dome. It relies on assumptions that just don't hold true in the real physical world. Your sources highlight several of these.
We already mentioned the frictionless surface and the perfect point particle.
Right. And then there's that crucial potential energy function itself, HR equals R42G. We talked about how it gives the dome a specific shape. Mathematically, realizing that exact shape at the apex, at R0, requires the surface to have a property called infinite differentiability right at that single point.
Infinite differentiability. What does that actually mean in, well, maybe not practical terms since it's unphysical, but what does it imply about the shape?
Infinite differentiability is a mathematical concept describing extreme smoothness. It means that not only is the function continuous, but its derivative slope is continuous, its second derivative curvature is continuous, its third derivative is continuous, and so on, infinitely. For a surface, it implies an incredibly smooth, perfectly rounded shape right at the very peak, whose curvature and higher order changes in shape vary in a perfectly smooth, continuous way as you move just an infinitesimal distance away.
Okay, super, super smooth mathematically.
Yes. And the argument from critics is that this is a purely mathematical property. You will never find it in any real-world material or surface. Physical objects are made of atoms, right? They have a granular structure at some level. Even the most highly polished mirror isn't infinitely smooth or infinitely differentiable at the atomic scale.
So a real physical surface just cannot have that exact mathematical shape required by the R4 function right at the peak.
Correct. Real materials have limitations. They have atomic structure, defects, finite stiffness. They can't conform to that perfect, infinitely differentiable point.
So the shape itself is inherently unphysical.
Precisely. And the model also conveniently ignores other practical constraints. It assumes the dome and the particle are perfectly rigid, ignoring any material properties like elasticity or tiny deformations under pressure. It assumes absolutely zero friction, not even the tiny residual friction or air resistance that always exists.
And crucially.
Crucially, it completely ignores quantum effects. Now, we usually say quantum effects are negligible for macroscopic objects like a ball on a dome, and that's generally true for overall motion. But when you're talking about behavior at a single mathematical point with this kind of infinite property, maybe quantum fuzziness or uncertainty principle effects might become relevant in preventing that perfect initial state or that infinitely differentiable shape from ever truly existing, even theoretically if you tried to build it atom by atom.
Okay, so the core argument against the paradox having real-world punch is that the dome isn't revealing a fundamental flaw in how physics works in reality. It's more like it's cleverly exploiting a loophole, or an edge case, in the mathematical model itself. A model that uses idealizations that don't perfectly mirror physical reality.
That's a key perspective, yes. Critics often argue it exploits mathematical corner cases. It finds these little loopholes that exist within the specific theoretical structure of the equations used to describe motion on this particular unphysical surface. They'd say it doesn't reflect the genuine flaw in physical reality or in how classical mechanics applies to the world we actually live in.
It's seen more as a consequence of choosing a mathematically, maybe pathological function, one with weird properties that cause the standard assumptions, like unique solutions, to break down.
Exactly. Rather than being a fundamental indictment of classical determinism as a whole, especially in its practical application.
That frames it very clear. It's like a philosophical brain teaser built using math, designed to make us think hard about determinism, rather than a genuine discovery about how actual balls behave on actual hills. So, what are the main debates and interpretations that have spun out from this?
Well, a lot of the debate constantly circles back to its physical relevance, or lack thereof. As we've really hammered home, real-world materials just cannot replicate that specific curvature and infinite differentiability needed at the apex.
So pretty much everyone agrees it's purely theoretical.
Yes. Physicists and philosophers largely agree it's a theoretical construct. You wouldn't expect to build one and see this happen. It's not an observable phenomenon in that sense.
Okay, so its main value is theoretical or philosophical, but even within that realm, you're saying there are different ways to interpret the non-uniqueness itself. People don't all agree on what it means.
Right, absolutely. There isn't one single consensus on the takeaway message. Some physicists and philosophers look at it and essentially say, look, the non-uniqueness is purely an artifact of choosing this very specific artificial and unphysical potential energy function.
Just a weird result from weird math.
Pretty much.
Yeah.
They argue it doesn't really tell us anything deep about inherent indeterminism in classical mechanics as it applies to the real world. For them, it's just a mathematical curiosity arising from a function that doesn't correspond to any force or situation found in nature. It's a breakdown in the math, not the physics of reality.
Okay, that's one view. What's the alternative interpretation?
Others take it more seriously as a conceptual point. They view it as a valid and important exploration of the conceptual boundaries within the mathematical framework of classical mechanics. They see it as demonstrating something important, that even within the classical framework, the mathematical conditions you actually need to guarantee strict determinism to ensure initial conditions always uniquely specify the future are perhaps more stringent, more subtle than we might have intuitively assumed.
So it shows where our gut feelings about determinism might break down in theory, Even if the specific scenario isn't physically possible, it makes us re-examine the mathematical foundations.
Exactly. It prompts a deeper look at what mathematical properties are truly necessary for a physical theory to be fully deterministic in all conceivable cases. It might show that simple continuity or basic differentiability isn't always enough. Maybe you need stronger mathematical conditions, like satisfying a Lipschitz condition, which Norton's dome violates at the apex, to guarantee uniqueness everywhere.
So it's less about a problem with physics describing reality and more about understanding the precise mathematical requirements for a model to be deterministic, especially when you push that model into extreme, idealized territory.
Yes, it forces a more rigorous examination of the mathematical underpinnings of our physical theories and the conditions under which they guarantee predictability.
Okay, so summing up this section on the dome itself, what does the source material suggest is the main takeaway?
The sources seem to conclude that Norton's dome is best understood as a provocative and important example, primarily within the philosophy of science. It definitely questions whether classical physics can be considered fully deterministic in the strictest mathematical sense, at least when you allow for these kinds of idealized, perhaps pathological scenarios.
But its practical implications are
Largely theoretical or philosophical, precisely because of its unphysical nature. However, because it's so counterintuitive and because it mathematically demonstrates this non-uniqueness, it has undeniably sparked significant discussion and debate.
about what specifically?
About the nature of causality, about how we define determinism and what its limits might be, and maybe most importantly, about the complex relationship between the mathematical models we use in physics and the physical reality those models are supposed to describe. It makes us think critically about whether our mathematical tools always perfectly capture the essence of physical law, especially when we push them to theoretical extremes.
So it's a powerful conceptual tool, a philosophical and mathematical probe for exploring the definition and boundaries of determinism, even if you can't actually build one in your garage to watch it happen.
That's a very good summary. It's a way to test the conceptual limits, the mathematical edges of classical mechanics using a very specific, carefully crafted mathematical construction.
Okay, that sets the stage beautifully for the dome itself and the surrounding debates. Now, let's tackle one of your really key questions from the sources, which takes us into a whole different realm of physics. Section 3. Bringing in quantum mechanics. Could this classical paradox somehow be explained away, or maybe fixed, by bringing quantum effects into the picture? You specifically asked if that spontaneous motion, the ball deciding to roll at some random time t, could actually be due to underlying quantum phenomena, maybe something like the probabilistic collapse of the wave functions that fundamentally make up the ball and the dome.
Yeah, this feels like a really natural and, frankly, quite insightful question to ask, doesn't it? We know classical physics seems to get weird with Norton's dome, and we know quantum mechanics is famous for introducing inherent randomness and probability into physics. So the thought is, maybe the apparent non-determinism in Norton's dome isn't really a classical problem at all. Maybe it's just a sign that underlying quantum effects are somehow bubbling up and becoming noticeable in this very specific, sensitive scenario.
Right, because at the quantum level, particles aren't really like tiny billiard balls with definite positions and velocities until you measure them. They're described by wave functions, which are all about probabilities.
Exactly. Wave functions give you the probability of finding a particle here or there with this momentum or that momentum. And the whole process of measurement in quantum mechanics, in the standard way of thinking about it, involves this inherently probabilistic collapse of the wave function, where all those possibilities suddenly resolve into one definite outcome.
So the idea you're exploring is maybe that ball sitting perfectly at rest on the dome's apex isn't truly classically at rest in a quantum sense. Maybe it's in some delicate quantum state, and a spontaneous quantum event, a random fluctuation, a wave function collapse somewhere in the complex system of atoms making up the ball and the dome is what actually triggers its motion at some unpredictable time t.
That's the line of thinking. Could quantum randomness be the real explanation for the apparent classical randomness?
But the sources you provided seem pretty clear, maybe even emphatic, that while this is a fascinating thought, it's generally not considered the correct or even the relevant explanation for the Norton's dome paradox as it was defined.
Wow.
Why not? Why doesn't bringing quantum mechanics into it just sort of fix the problem or explain it away?
The main reason, which the sources really emphasize, comes down to the vast difference in scale. Quantum effects, things like quantum uncertainty, superposition, tunneling, are typically dominant and readily observable at microscopic scales, like individual atoms or electrons. but they are usually considered utterly negligible at the macroscopic scales involved in Norton's dome.
We're talking about a ball, even a tiny one, on a dome structure. Things we can imagine seeing and interacting with using classical physics concepts like force and friction, or lack thereof.
Exactly. These are macroscopic objects by physics standards. And for such large objects, a process called decoherence becomes incredibly important.
Decoherence. Can you remind us what that is?
Decoherence is basically the process by which a quantum system loses its quantum properties, its ability to be in multiple states at once, superposition, or be linked with other systems, entanglement, due to its interactions with the surrounding environment.
Like interactions with air molecules, thermal vibrations within the material of the dome itself, even stray photons of light bouncing off it.
Precisely. All those tiny interactions constantly measure the state of the macroscopic object, forcing it very, very quickly to settle into a state that looks classical.
Yeah.
These interactions effectively suppress any significant quantum weirdness in large objects, making them behave according to the predictable, usually deterministic, rules of classical physics.
So the idea of the macroscopic ball just sitting there indefinitely in some fragile quantum superposition of at rest and about to start moving spontaneously due to quantum jitters is just not physically realistic. The environment would kill that superposition almost instantly.
That's the standard understanding based on decoherence theory. It's incredibly difficult to maintain quantum coherence in large, warm, interacting systems like a ball on a dome. Also, think about the mass and energy scales involved.
Sure.
The amount of energy required for a purely quantum fluctuation, or maybe a quantum tunneling event, where the ball somehow tunnels through a tiny energy barrier right at the peak, to actually move a macroscopic ball, even a tiny one, perceptibly against the force of gravity and start it rolling down the dome. Well, the probability of such an event is typically calculated to be astronomically small. It's just not considered a plausible physical mechanism for triggering the kind of spontaneous macroscopic motion described by the classical paradox. The energy scales are wrong.
Okay, so decoherence and energy scales argue against a quantum explanation being physically relevant here. But just for the sake of argument, purely hypothetically, as a way to really nail down the distinction between the classical paradox and quantum effects. If we did try to apply quantum mechanics rigorously to the Norton's dome scenario, what might that look like? And would it actually resolve the non-determinism issue?
Well, if you were to hypothetically construct a full quantum mechanical model of the ball and the dome, the initial state wouldn't be particle at arcule 0 with velocity 0. It would be represented by a complex wave function, probably highly peaked around arcule A00 momentum, but with some inherent quantum uncertainty or spread.
So not perfectly localized?
Right. Now, if some interaction or measurement occurs may be described as a collapse of that wave function, it could theoretically lead to the particle suddenly having a definite position slightly off the apex, or a definite momentum pointing away from the apex, and that would cause it to start moving.
Okay, so QM could, in principle, lead to movement.
Yes, but here's the crucial point again. In standard interpretations of quantum mechanics, that collapse process is inherently probabilistic. Quantum mechanics wouldn't tell you exactly when the collapse would happen or exactly what the outcome, the specific position and momentum after collapse would be. It would only give you probabilities for different outcomes.
Which means it still wouldn't predict a single unique future from the initial state. It would predict a whole range of possible futures, each with a certain probability attached.
Precisely. So you haven't actually resolved the issue of non-determinism in the sense of getting a unique prediction. You've just replaced a situation of potential classical non-determinism, where the classical math itself allows multiple futures, with the inherent quantum indeterminism, where the future is fundamentally probabilistic according to the laws of QM.
And that brings us back to the core argument from the sources, right? Norton's dome, the paradox itself, is defined and exists entirely within the conceptual and mathematical framework of Newtonian mechanics. The paradox, the non-unique solutions, arises purely from the mathematical structure of the classical equations when applied to that specific weird, unphysical potential function that Norton chose.
Exactly. So if you introduce quantum mechanics, you're fundamentally changing the rules of the game. You're changing the framework you're working in. You're not resolving the paradox within its original context, which was all about the limits and properties of classical physics and its mathematical description.
It's like you said before, it's like trying to solve a tricky problem in the rules of chess by suddenly bringing in the rules of Go. You're not solving the original chess problem, you're just playing a different game with different rules and different kinds of outcomes.
That's a really good analogy for it. Bringing QM into the Norton's dome discussion essentially shifts the focus away from the specific theoretical challenge it poses to classical determinism and towards the well-known but fundamentally different issue of inherent indeterminism that exists in quantum mechanics. The sources emphasize that these are distinct sources of non-determinism or unpredictability, arising from different levels of physical description.
And besides, even if you brought in quantum mechanics, it wouldn't magically make the unphysical mathematical idealization of the dome itself suddenly physically realizable, would it? The problem with needing that infinitely differentiable shape at the apex would still be there.
Absolutely correct. Quantum mechanics provides a different, more fundamental set of rules for how particles behave, especially at small scales. But it doesn't change the purely mathematical definition of Norton's dome surface. It doesn't make that specific R4-2G potential function correspond to any real physical material or interaction.
Yeah.
That idealization remains purely mathematical.
Okay, so let's try to nail down the conclusion on this quantum connection then. The sources seem to strongly reiterate. Norton's dome is a classical paradox. It arises purely from the structure of classical mathematics under very specific, idealized, and unphysical conditions. It's not secretly a quantum phenomenon in disguise. Quantum mechanics does introduce indeterminism into physics, absolutely, but it's a different kind of indeterminism, operating under different rules and at different scales. And it's considered unrelated to the specific mathematical non-determinism found in the formulation of Norton's dome.
Yes, the two issues are distinct.
So quantum effects are not seen as a relevant fix or a necessary explanation for the Norton's dome thought experiment. Trying to apply them just shifts the framework away from the original point, which was about exploring the limits of determinism within the classical picture itself.
Precisely. The paradox of Norton's dome highlights a conceptual boundary, a theoretical edge case, found within classical mechanics' mathematical structure, not necessarily a point where classical mechanics fundamentally breaks down in a way that requires a quantum explanation for that specific theoretical scenario.
Got it. The puzzle really lives and breathes and maybe dies purely within the theoretical realm of classical math and its philosophical implications, even if the scenario itself could never actually happen in the real world.
Exactly. It's all about what the established mathematics of classical physics allows in a purely hypothetical constructed situation, not about reporting a real-world failure of classical physics that demands a quantum resolution.
Okay, that distinction is super important, which leads us very logically to your next big question, following right on from that. Section 4. Is Newtonian physics flawed? And this whole idea of unification, you asked quite recently, doesn't this non-determinism shown by Norton's dome, even at theoretical, just add fuel to the fire? Doesn't it support the broader idea that Newtonian physics is fundamentally an inherently flawed or incomplete model anyway? And shouldn't we therefore need to bring in our better theories like quantum mechanics, or maybe even unify classical and quantum models, just to properly explain what's going on, even in this abstract scenario?
Yeah, it's a very tempting conclusion to jump to, isn't it? If you find a situation, even a purely theoretical one, where your classical physics model seems to break down or become non-deterministic, doesn't that just prove that the model itself is flawed at a fundamental level? Doesn't it show it's incomplete and needs to be superseded or at least integrated with our more fundamental theories like quantum physics, even just to understand why this abstract problem arises?
It seems logical. If the rules fail in one case, maybe the rules themselves are the problem. But the sources you provided seem to push back on this quite firmly. They offer a pretty strong no to the idea that Norton's dome somehow invalidates Newtonian physics as a useful model.
That's right. The sources are quite clear on this point. No, Norton's dome does not invalidate Newtonian physics or demonstrate a practical flaw in it. And really understanding why this distinction is made is critical if we want to grasp the true, perhaps more subtle, significance of the dome paradox.
Okay, so why is that distinction so crucial? I mean, Newtonian physics failed to predict a unique future in this theoretical case. That sounds like a pretty significant issue for a theory that's often held up as the prime example of deterministic physics.
It's crucial because we need to remember just how incredibly successful Newtonian mechanics is within its intended domain of application. For describing the motion of macroscopic objects, things much larger than atoms, under conditions far from the speed of light or extreme gravity, it works spectacularly well.
Like calculating planetary orbits with amazing precision.
Exactly. Predicting how a real ball rolls down a real hill, engineering bridges and buildings, launching spacecraft to other planets. For all these things, Newtonian physics is an incredibly accurate, reliable, and predictively powerful model. It is absolutely not a flawed model for the vast majority of situations we encounter and apply it to in the real world.
Okay, fair enough. It works great for almost everything we use it for. But what about the dome itself? Even if it's theoretical, if the theory breaks its own rules of determinism in that specific case, doesn't that point to a flaw in the theory's claim to universality, or at least its completeness?
Here we have to circle back to what the dome is. Remember, as we've stressed, the dome is a mathematical abstraction. It's not a physical object that exists or even could be built in reality. It was specifically designed as a thought experiment precisely to test the theoretical limits of classical determinism. And it only succeeds in doing so by invoking very specific, highly idealized, and ultimately unphysical assumptions.
Ah, okay. So you're saying the paradox isn't really a problem inherent to Newtonian physics when it's applied to describe the real world. It's more like a problem or a weird outcome that emerges only when you apply Newton's laws to a piece of theoretical mathematics that doesn't actually correspond to anything physically real.
That's exactly the perspective the sources seem to advocate. The paradox arises directly from those idealized unphysical assumptions that artificial potential function with its R4 dependence, the requirement of infinite differentiability at the apex, the perfect absence of friction and other real-world factors. It exposes a theoretical edge case, a kind of mathematical loophole or breakdown point that exists within this specific idealized mathematical framework, not a fundamental break or flaw in Newtonian physics itself, as it applies to the real world we experience and measure.
So it shows where the mathematical formalism might get weird or fail to guarantee uniqueness under extreme, arguably fictional conditions, but doesn't mean the physics model itself is broken for describing actual physical things.
Precisely. It demonstrates where the mathematical guarantees of determinism might fail under extreme non-physical conditions, not where the physics as a description of reality fails us in general practice.
Okay, that makes sense. Now, what about the second part of the question? The idea that maybe we need to unify classical and quantum models to explain this, even if it's abstract.
Well, it's absolutely true that unifying classical mechanics, especially Einstein's theory of gravity, general relativity, with quantum mechanics, is one of the biggest, most important, and still unresolved challenges in fundamental physics.
The search for a theory of everything, or at least a consistent theory of quantum gravity.
Exactly. Physicists are working intensely on frameworks like string theory, loop quantum gravity, and other approaches precisely because we need such a unified theory to describe situations where both gravity and quantum effects are undeniably important and interact strongly.
Like understanding what happens inside black holes, or describing the universe in the very first moments after the Big Bang, or perhaps exploring the fundamental nature of space-time itself at the tiniest possible scales, the Planck scale.
Absolutely. That unification is considered crucial for pushing the frontiers of physics in those extreme regimes where our current separate theories of gravity and quantum mechanics are expected to break down or give conflicting answers. However, the source material argues quite strongly that Norton's dome is not one of those situations. It's not a practical physical scenario that actually requires such unification.
Why not? Because it's not a real-world situation where we see macroscopic and microscopic effects clashing in a way that only a unified theory could describe.
Precisely that.
Yeah.
Norton's dome is a thought experiment. It was created specifically to explore a philosophical point about classical determinism using the tools and concepts of classical mathematics. It's firmly rooted in the philosophy of classical physics, not in experimental physics that has uncovered a real breakdown of classical laws in a physical system that points towards the need for quantum gravity.
So trying to bring in quantum mechanics or quantum gravity to explain Norton's dome wouldn't actually make the dome physical, and it wouldn't resolve the paradox within its original classical context. It would be overkill, misapplied.
Kind of like saying that because Newtonian mechanics doesn't accurately describe the quantum behavior of electrons inside an atom, the only way we can understand why a bowling ball stays on a normal macroscopic hill is by invoking quantum field theory. It's applying a much more complex and fundamental theory to a problem that was specifically defined and arises within a simpler, less fundamental framework. It obscures the original point being made about the classical framework itself.
Okay, so let's try to summarize this section again. What does Norton's dome really show us, according to these sources, if it doesn't mean Newtonian physics is fundamentally flawed in practice?
What it primarily represents is a philosophical challenge to the notion of strict, universal Laplacian determinism based on classical laws alone. It serves as a stark illustration of a potential limitation or edge case of the mathematical models used in classical physics, specifically when those models are pushed to incorporate extreme, unphysical idealizations.
And it makes us think more deeply
About the relationship between physical reality and the mathematical abstractions we invent and use to describe it. It forces us to consider whether our mathematical descriptions always perfectly capture physical behavior, especially at theoretical extremes. But, and this is the crucial but, it does not mean that Newtonian physics is broken or unreliable for its intended purpose. Accurately describing the vast majority of physical phenomena in the macroscopic world we interact with every day.
So, conclusion. Norton's dome is a fascinating theoretical edge case. It highlights where classical mathematical models might fail to guarantee determinism in theory under artificial, unphysical conditions. But it's not evidence of a flaw in Newtonian physics that requires quantum unification to explain it within its own classical context.
That's the key takeaway presented in the sources. It's a demonstration of a mathematical curiosity, a property of a specific differential equation arising from an artificial potential within classical mechanics' theoretical framework. It's not a signal that we need a whole new fundamental theory of everything just to understand why hypothetical balls might or might not roll down hypothetical weirdly shaped hills.
Okay, that really clarifies the dome itself and its place relative to both classical and quantum physics and the idea of unification. Now, you had another really excellent comparison point in your sources, which takes us nicely into Section 5. Comparing Norton's dome to Lagrange points, you asked a very interesting question. How does Norton's dome compare to something like a Lagrange point in a gravitational system? After all, an object placed exactly at a Lagrange point is also in equilibrium, experiencing zero net force, just like the ball at the peak of the dome. So does this similarity mean Lagrange points might have similar issues with determinism, or maybe with time reversal symmetry when trying to figure out an object's origin?
Yeah, this is a great comparison to explore because at first glance they seem to share that really key feature. They both represent points in space where an object can theoretically be perfectly at rest, in a state of stable or perhaps quasi-stable equilibrium, because the net force acting on it is zero right at that point.
Before we dive into the comparison, maybe let's quickly define Lagrange points again, just for anyone listening who might not be familiar with them.
Sure. Lagrange points, which are often labeled L1, L2, L3, L4, and L5, are specific locations in space relative to two large orbiting bodies. The classic example being the Sun and the Earth, or perhaps the Earth and the Moon. They are special points where the gravitational forces from the two large bodies combine precisely with the centrifugal force that an object feels in the rotating reference frame of the system.
And this combination of forces creates points of equilibrium.
Exactly. It creates points where the net force on a third, much smaller object like a satellite or an asteroid is zero relative to the two large bodies.
So if you place a smaller object, like a spacecraft, precisely at one of these Lagrange points, it can essentially hover there, maintaining its position relative to the two larger bodies with very little fuel needed for station keeping.
Precisely. We use them strategically for exactly that reason. Things like the James Webb Space Telescope is parked out at the Sun-Earth L2 point, as Soyuz spacecraft monitors the Sun from L1. There are points of stable, L4, L5, or quasi-stable, L1, L2, L3, equilibrium.
And importantly for our discussion, these points and all their properties, their locations, their stability, are mathematically derived directly from Newton's laws of gravitation and motion, right? The same classical framework that we were discussing for Norton's dome.
Absolutely. They are a direct consequence of applying Newtonian mechanics to the gravitational interactions in typically what's called the restricted three-body problem.
Okay, so now let's get back to the comparison you raised. What are the similarities you identified between a Lagrange point and the apex of Norton's dome? Both involve an object at rest in equilibrium.
As you just pointed out, the most obvious similarity is that both scenarios involve theoretical equilibrium points, where an object can, in principle, be perfectly at rest because it experiences zero net force. And you could argue both scenarios often involve idealizations in practice. For instance, when we analyze Lagrange points, we might initially ignore the gravitational pull of other planets or the pressure from solar wind just to simplify the math.
Similar to how Norton's dome idealizes away friction and material properties.
Right. Although it's crucial to remember, as the source clarifies, that while the absence of friction is part of the setup for the dome, it's not the cause of the non-deterministic paradox itself. The paradox comes from the specific mathematical structure of the potential function at the apex. Whereas for Lagrange points, ignoring other forces is just a simplification, not the source of their fundamental behavior. The main point of comparison here is really just the existence of that state of equilibrium.
Okay, understood. The dome's paradox is fundamentally tied to the math of its specific shape, not just the general idealizations like zero friction. So, where do they differ most fundamentally? Why are Lagrange points considered fully deterministic in their behavior, even if predicting long-term orbits can be complex due to chaos theory? While the dome exhibits this theoretical non-determinism right at the equilibrium point.
The crucial differences lie in two main areas. First, the fundamental source of the potential energy that creates the equilibrium point, and second, as a direct consequence of that, the resulting mathematical behavior of the equations of motion near that point.
Let's take the source first. Where do Lagrange points come from versus the dome?
Lagrange points arise from real physical gravitational forces between actual massive objects like the Sun and the Earth. It's a natural gravitational phenomenon. The equilibrium is real, derived from Newton's universal law of gravitation.
Okay, real physics. And the dome.
As we've established, the dome's equilibrium point at the apex exists because of an artificial mathematical construct. That potential energy function, HR equals R42G, was invented specifically to create the paradox. It doesn't represent a real physical force or interaction found in nature.
So, real gravity versus artificial math. How does that difference lead to different mathematical behavior regarding determinism?
Because Lagrange points arise from standard Newtonian gravity, the equations describing motion near them are derived from deterministic Newtonian laws. Specifically, the equations for the restricted three-body problem. These equations, while complex, are fully deterministic. They do not produce non-unique solutions from a given initial condition. If you know the exact position and velocity of an object near a Lagrange point at one time, Newton's laws uniquely predict its future trajectory.
Whereas the dome's equation, d2 dt22 equals gr, specifically has those non-unique solutions for the special initial condition of being exactly at rest at the apex, r00, rdt is 00.
Yes, that's the critical mathematical difference. The non-uniqueness is baked into the mathematical structure of the dome's governing equation, specifically for that singular point and initial state. There's another related difference, too, in how they respond to small disturbances.
How so?
At Lagrange points, if an object is slightly perturbed from the exact equilibrium point, its subsequent motion is entirely predictable based on Newtonian mechanics. Depending on which Lagrange point it is and the nature of the perturbation, the object might oscillate around the point in a stable way, like near L4 and L5, which are potential wells, or it might slowly drift away in a predictable manner, like from L1, L2, and L3, which are saddle points in the potential. These deviations are calculated precisely and deterministically.
Okay, predictable response to small pushes. And the dome?
The dome's non-uniqueness is different. It's purely mathematical and, in the idealized model, can theoretically occur without any external perturbation whatsoever. The particle could just spontaneously start moving at an arbitrary time, purely due to the nature of the mathematical solution itself, not because of an external nudge.
Okay, that distinction is very clear. One is a predictable equilibrium point arising from real forces within the standard deterministic framework of Newtonian physics, while the other is an unphysical mathematical setup specifically engineered to violate forward determinism mathematically right at the equilibrium point. But you also raised a really interesting follow-up point about time reversal symmetry and figuring out an object's origin. If we find an object sitting perfectly still at a Lagrange point, can we use the time reversibility of physics to uniquely figure out how it got there?
This is where your question digs into a different but equally fascinating kind of ambiguity or unpredictability, one related to reconstructing the past, which is distinct from the dome's paradox about predicting the future.
Remind us about time reversal in classical mechanics.
Okay, so classical mechanics, the fundamental laws, like Newton's laws or Hamilton's equations, are generally considered time reversible. This means that the laws themselves work just the same, whether time flows forwards or backwards. If you were to watch a movie of a purely classical system, like billiard balls colliding without friction, the reversed movie would also depict a physically possible sequence of events according to the same laws. In principle, this means that knowing the precise state of a system, all positions and all velocities, at one specific time, should allow you to perfectly reconstruct its entire past history. You just reverse all the velocities in your equations of motion and run the simulation backwards in time.
Okay, so in principle, time reversal should work. So let's apply that. Suppose we find a satellite perfectly exactly at rest relative to the Earth and Sun at the L1 Lagrange point. Can we just hit the rewind button on our simulation and see exactly where it came from, say, tracing it back to a specific launch pad on Earth at a specific time?
And this is where you correctly identified a potential problem with uniquely reconstructing the past. But it's crucial to see it's a different kind of problem than the dome's non-determinism about the future. The issue is, if an object is found exactly at rest at a Lagrange point, we often cannot use time reversal to uniquely determine its specific entry path or its precise origin in the distant past.
Why not, if the laws are time reversible?
Because, as you hinted, multiple different past trajectories could have hypothetically led the object to arrive at that specific L1 point with precisely zero relative velocity at that precise moment in time. Maybe it was carefully maneuvered there from Earth orbit, maybe it arrived on a complex looping trajectory influenced by the Moon or other planets, maybe it was an asteroid captured into that state. Many different initial conditions in the past could, in principle, evolve forward in time to result in the same final state of being perfectly at rest at the Lagrange point at time t.
Ah, I think I see. It's not that the fundamental laws of physics are breaking down or allowing multiple pasts from one present. It's more like the information about the specific past trajectory gets lost or compressed when the object reaches that perfect equilibrium state. We don't have enough information in that final state alone to distinguish between all the possible histories that could have led there.
That's exactly it. It's what mathematicians and physicists often call an underdetermined inverse problem. The forward problem in classical mechanics, predicting the unique future state from known initial conditions, is typically well posed and deterministic, except for pathological cases like Norton's dome. But the inverse problem, trying to uniquely reconstruct the precise initial conditions, like a launch point and initial velocity vector, from knowing only a single state later in time, especially a static equilibrium state like being perfectly at rest at the Lagrange point, may not be uniquely solvable.
Because multiple different starting points could converge onto the same endpoint.
Precisely. And think about time reversal, specifically for the state at rest. What happens if you reverse a velocity of zero?
It's still zero.
Right. The equilibrium state of being at rest is invariant under time reversal. So if all you know is that the object state is at rest at the Lagrange point at time t, simply reversing time mathematically just tells you its state was at rest at the Lagrange point at time t minus dt. You don't get a unique trajectory stretching back into the past from that information alone. It's a case where the system reaching equilibrium has effectively caused a loss of information about its specific history. The details of how it got there are no longer encoded in its present state of just being at rest.
Okay, that is a really crucial distinction. Let me see if I've got it. Norton's dome demonstrates a theoretical non-uniqueness in the forward prediction problem. The math seems to allow multiple possible futures to spring from identical initial conditions. Lagrange points, on the other hand, when we consider an object found perfectly at rest there, highlight a potential ambiguity in the inverse problem of reconstructing the past. Multiple possible histories could have converged to the same final equilibrium state, primarily because that state itself doesn't contain enough information to uniquely specify its past trajectory.
You've nailed it. They both challenge our simple intuitions about determinism and predictability, but in fundamentally different ways. One challenges the uniqueness of the future, given the present, forward determinism, due to a pathological mathematical setup. The other highlights the potential non-uniqueness of the past, given the present, inverse problem ambiguity, often due to reaching an equilibrium state where historical information is effectively erased or becomes ambiguous.
That distinction between the forward prediction problem and the inverse reconstruction problem, and how each scenario highlights a different kind of challenge or ambiguity, is really key to understanding why they aren't the same kind of issue. One is about what the math theoretically allows going forward. The other is about the information available in the present state traced backward.
Yes, exactly. And Norton's dome's challenge, being purely theoretical, is specifically aimed at that forward prediction piece within the mathematics of classical mechanics. The Lagrange point question, while also theoretical in the sense of achieving perfect rest, relates more to the practical and informational limits of reconstructing history from a specific static final observation.
Okay, brilliant. That comparison really helps clarify the unique nature of the dome paradox. Now, this leads you to one further refinement of the idea in Section 6, where you revisited the potential energy. You asked, could the fundamental difference between Lagrange points in the dome ultimately boil down to the type of forces creating the potential energy surface? You had this idea. Maybe Lagrange points are purely gravity, resulting in maybe a net zero potential energy landscape in some sense. Whereas the dome might involve gravity pulling down plus some kind of repulsive force pushing up, maybe related to the atomic structure of the surface material.
Yeah, it was an attempt to find a more physical grounding for why these two scenarios, both involving equilibrium, behave so differently when it comes to determinism. Is it fundamentally about the nature of the forces involved? Gravity versus something else?
It's a good instinct to look for a physical explanation, so let's clarify the sources of potential energy in each case, based on the information in the source material we have.
Okay, first, Lagrange points. As we established, the potential energy landscape that defines the Lagrange points is purely gravitational in its origin. It's derived entirely from the gravitational forces exerted by the two large primary bodies, like the Sun and the Earth. The equilibrium occurs where these gravitational forces precisely balance the inertial force, the centrifugal force, that arises in the rotating reference frame we use to describe the system. It's a phenomenon rooted entirely in Newtonian gravity.
And importantly, you mentioned no repulsive forces are involved in defining the Lagrange points themselves.
Correct. The standard derivation involves only gravity and the inertial centrifugal force. There's no atomic repulsion or contact force built into the definition of the Lagrange points in space.
Okay. And just to clarify the point about potential energy being zero, achieving that balance of forces at the Lagrange point, does that mean the potential energy value is zero there?
Not necessarily zero in an absolute sense, like compared to being infinitely far away. What equilibrium means in terms of potential energy is that the gradient, which is like the slope or steepness, of the total effective potential energy function is zero at that point. That's the mathematical definition of an equilibrium point. The net force, which is related to the gradient of the potential, is zero. So the potential energy landscape is flat, right at the Lagrange point. It has an extremum. There could be a peak, like L1, L2, L3, which are unstable saddle points, or a dip, like L4, L5, which are stable potential minima. But the actual value of the potential energy at that point relative to some reference, like infinity, is generally not zero.
Got it. Zero force means zero slope on the potential energy graph, not necessarily zero height. Okay, so that's Lagrange points. Pure gravity plus inertia creating equilibrium points where the potential gradient is zero. Now, what about Norton's dome? Does that potential energy function, HR over R42G, somehow represent a combination of gravity pulling down and a repulsive force from the material atoms pushing up?
This is where we need to be really clear, based on the source material, and correct that intuition. The source material is quite firm. The potential energy function HR equals R42G that defines Norton's dome is purely a mathematical construct. It is not derived from, nor is it intended to represent, any combination of known physical forces like gravity pulling down and, say, electromagnetic or atomic repulsion from the surface pushing up.
Ah, okay. So the idea that the dome's shape might physically arise from balancing gravity with some kind of real-world repulsive force, that's actually not part of the official Norton's dome model at all.
Not at all. There might be an intuitive way someone could imagine trying to physically create a dome-like surface, perhaps, but the Norton's dome thought experiment is defined purely by stipulating that specific mathematical potential energy function. Its existence and properties flow entirely from that mathematical definition, which was chosen precisely because it generates the non-unique solutions and thus the paradox. There is no underlying model of physical interactions, gravity, electromagnetism, strong or weak nuclear forces, atomic repulsion, none of that naturally combines to create that specific HR equals R42G potential near the apex.
Okay, that is a really critical clarification. The source of the potential energy in Norton's dome isn't physical forces, it's just abstract mathematics chosen for a specific non-physical outcome.
Exactly. It's a function selected purely for its peculiar mathematical properties at RO0. Namely that it leads to a differential equation that violates the standard conditions like the Lipschitz condition, needed to guarantee unique solutions for the given initial state.
So that core distinction we established earlier between Lagrange points and the dome really holds true and is even deeper than just real versus theoretical. It's about the fundamental origin of the governing potential.
Yes, and it seems to be the fundamental reason for their drastically different behavior regarding determinism. Let's recap that core distinction one last time.
Arise from a natural physical phenomenon, gravity between massive bodies plus inertia in a rotating frame. They lead to predictable deterministic equilibria, though long-term stability can be complex, fully described by standard deterministic Newtonian laws applied to real forces.
An artificial mathematical model designed purely to reveal a theoretical limit or loophole in classical determinism. It's based on an abstract, unphysical potential function chosen specifically for its mathematical properties that lead to non-unique solutions at the apex.
So, they differ critically in their very origin. One arises naturally from real physics. The other is a mathematical invention constructed deliberately to make a philosophical point about the limits of deterministic math. And that fundamental difference in origin seems to fully explain why one behaves deterministically in its forward evolution, Lagrange points in the real world, and the other exhibits mathematical non-determinism in its purely theoretical description, Norton's dome, despite the superficial similarity of both having an equilibrium point where the net force is initially zero.
Exactly. The nature and, crucially, the source of the potential energy function are the defining features. In Norton's dome, that source is pure mathematical stipulation, specifically chosen to break determinism, not a description of any known physical forces or interactions.
Okay, wow. We have really explored Norton's dome now from multiple angles. What it is, the paradox, the critiques, why quantum mechanics doesn't really fix its classical problem, and how it differs fundamentally from real physical equilibrium systems like Lagrange points. This incredibly deep dive into the weeds of classical determinism, its limits, and its mathematical underpinnings naturally, almost inevitably, leads us to one of the most profound, persistent, and personal questions that philosophy and science grapple with, question you also raised directly in your sources: the question of free will. So let's transition now into Section 7 and start exploring free will in light of everything we've discussed about determinism, the potential role, or lack thereof, of quantum mechanics, and the very nature of thought and observation itself.
Yes, this is where these seemingly abstract theoretical discussions about determinism and physics suddenly become very intimate and start bumping up against our own subjective experience of making choices, of feeling like we have agency in the world.
Let's start with the classical picture. In a universe that is governed by strictly deterministic laws, like the one envisioned by pure classical Newtonian physics, if we set aside the highly theoretical, unphysical Norton's dome edge case for a moment, in that kind of clockwork universe where the future state of everything is, in principle, fully and uniquely predictable from the past state based on immutable physical laws, what happens to free will? At least free will as it's commonly understood.
Well, free will in the common sense, often called libertarian free will, usually implies the genuine ability to have chosen otherwise. It means that when you made a decision, there were real alternative possibilities open to you, and your choice wasn't simply the inevitable outcome of prior physical causes stretching back in time.
The feeling that I could have picked the other option.
Exactly. And in the strictly deterministic Newtonian universe, that kind of free will seems to have no place to exist. It appears to be either completely non-existent or perhaps just a compelling illusion generated by the complexity of our brains.
Because if determinism holds true right down to the atoms in my brain,
then every thought you have, every desire you feel, every deliberation you undertake, and every action you ultimately take is simply the necessary, inevitable consequence of the physical state of your brain and body just moments before, which in turn was the inevitable consequence of the state before that, and so on, tracing back in an unbroken chain of physical cause and effect, potentially all the way back to the Big Bang.
So my choices wouldn't be truly mine in the sense of originating from some independent self. They'd just be the playing out of physics.
That's the stark conclusion of hard determinism. It makes finding conceptual space for genuine freedom of choice, in that libertarian sense, incredibly difficult, if not impossible. Your actions would be determined by physics, full stop.
Now, you mentioned in the sources a philosophical stance called compatibilism. How does that try to square this circle?
Compatibilism takes a different approach. It's the philosophical position that argues free will can actually exist, even if the universe turns out to be completely deterministic.
How can both be true? Freedom and determinism.
Compatibilists achieve this typically by redefining what they mean by free will. Instead of requiring that our actions be uncaused or that we could have genuinely done otherwise in exactly the same circumstances, they often define free will differently. For example, they might define it as the ability to act according to your own conscious desires, reasons, and intentions without being externally coerced or constrained.
So even if my desires and intentions were themselves ultimately determined by prior causes and the laws of physics,
as long as my actions flow from those internal states, my desires, my beliefs, my character, rather than being forced upon me by someone else or some external factor, then according to compatibilism, I am acting freely and can be held morally responsible.
So under this view, freedom isn't about breaking the causal chain. It's about whether your actions originate from your own internal psychological states, regardless of how those states themselves came about. It's about internal control and authorship versus external coercion.
Precisely. It focuses on the source of the action being internal to the agent's mental states, even if those states are part of the deterministic unfolding of the universe. It's a very influential philosophical approach because it seems to reconcile our strong intuition that we do make choices and are responsible for them with the scientific picture of a universe potentially governed by deterministic or perhaps statistically deterministic laws.
Okay, that's compatibilism, redefining free will to fit within determinism. But what if you don't accept that? What if you really hold on to the idea that for a choice to be truly free, it must involve genuine indeterminism? It must be the case that given the exact same past circumstances, you genuinely could have chosen differently. If you hold that view, then classical physics, being largely deterministic, again, ignoring Norton's dome is irrelevant here, seems to rule out free will.
Correct. If your definition of free will indeterminism requires that the future wasn't fixed by the past at the moment of choice, then the mostly deterministic picture painted by classical physics seems incompatible with it.
And this is where quantum mechanics, with its famous inherent randomness and probability, often enters the free will debate, right? As a potential physical source for the required indeterminism.
Exactly. If you think genuine free will needs some physical wiggle room, some indeterminacy in the unfolding of events, then the fundamental probabilistic nature of quantum mechanics seems like the most obvious place in our current understanding of physics to look for it. Quantum mechanics does seem to introduce genuine randomness into the universe at its most fundamental level.
Like in the exact moment a radioactive atom decays, or the specific outcome you get when you measure the spin of an electron that was in a superposition. These seem genuinely unpredictable, even in principle.
According to standard interpretations, yes, they are fundamentally probabilistic.
So the thinking goes, could this quantum randomness somehow get amplified? Could it bubble up from the micro level of atoms and molecules and actually influence the electrochemical processes happening in our brains at a critical level, perhaps tipping the scales in our decision-making processes? Could a specific decision, choosing coffee over tea, say ultimately hinge on a truly random quantum event happening within a key neuron or a network of neurons?
It's a really compelling idea and has been explored by various thinkers and scientists. Some have proposed specific mechanisms for how quantum effects might be amplified in the brain to influence thought. However, the sources you provided, and indeed the majority view in contemporary neuroscience and physics, urges significant caution here.
Why the caution?
Primarily for the same reasons we discussed when considering quantum effects in Norton's dome, the issue of scale and decoherence. Brains, despite being made of quantum particles, are generally considered macroscopic systems when we talk about the level of neural networks and cognitive processes.
They're warm, wet, complex environments.
Exactly. And as we discussed, decoherence, the constant interaction of the system with its environment, is expected to be incredibly rapid and effective in such systems. While quantum events are certainly happening constantly at the atomic and molecular level within our neurons, in chemical reactions, ion channel openings, etc., the dominant view is that these effects are very likely averaged out, smoothed over, or washed away by decoherence long before they could have a significant coordinated impact on the large-scale firing patterns of thousands or millions of neurons that are thought to underlie conscious thought and deliberate decision-making.
So the consensus is leaning towards the idea that the brain, at the functional level of thought, behaves essentially classically, even if it's built from quantum components. Quantum noise might just be noise, not a driver of choice.
That's the prevailing view, although it's still an area of active research and debate. It's debated whether quantum effects play any significant, non-trivial, and functionally relevant role in conscious decision-making at the macroscopic level where our thoughts seem to operate. Many suspect they don't, and that the brain's information processing is fundamentally classical, perhaps with some random noise that isn't necessarily quantum in origin either.
Okay, so that's one major challenge. Getting quantum effects to significantly influence macroscopic brain function. But even if they did, you raised another really significant philosophical hurdle in your sources. Does randomness actually equal freedom?
That's perhaps an even deeper philosophical problem.
Yeah.
Let's imagine, for argument's sake, that your decision to pick the coffee this morning was directly caused by a random quantum fluctuation in a critical neuron in your brain. Is that outcome really what we mean by free will?
It doesn't feel like it. It
Yeah.
feels more like my choice was arbitrary, subject to a coin flip at the quantum level.
Exactly. Free will, as we usually experience it or value it, seems to involve more than just randomness. It implies a sense of conscious control, rational deliberation, acting for reasons, a sense of authorship over our actions that aligns with our character and values. A purely random event, even if it happens inside my head, doesn't seem to fit that description. An action caused by a random quantum event is certainly not deterministic, but is it a choice made by a rational, conscious self? Or is it just something unpredictable that happened to me?
So simply swapping classical determinism for quantum randomness doesn't necessarily bias the kind of free will we intuitively feel we have. Randomness isn't the same as agency.
Yeah, it's a very common and powerful philosophical objection to purely quantum-based accounts of libertarian free will.
This whole discussion then leads us directly into the incredibly deep and insightful paradox, or maybe dilemma, that you pose in your sources. A question that really pushes the boundaries of our current understanding of mind, matter, and measurement, you asked. Is thought itself an emergent property, something that arises from the complex physical system of the brain that can then somehow act back on the physical world, perhaps by constituting an observation that could cause wave functions to collapse in a non-deterministic way? Or is the alternative true? Are thoughts themselves simply a deterministic property that arises as a result of external observation and the subsequent physical processing in the brain? And if so, determined by what external process or entity? This question seems to throw us right into the heart of the ancient mind-body problem and the notoriously difficult measurement problem in quantum mechanics.
Yes, this is where we've really hit the wall, or perhaps the edge, of what contemporary science and philosophy can confidently say. We're wading into the deepest, most uncertain waters here, where physics, philosophy of mind, and consciousness studies all intersect and often conflict. Let's try to unpack the first part of your dilemma. The idea of thought as an emergent property that might have causal power, perhaps even related to quantum measurement.
Okay. We often talk about emergent properties in science, right? Complex systems can definitely exhibit properties that aren't obviously present in their individual components.
Absolutely. Think about the wetness of water. It's a property of a vast collection of H2O molecules interacting in certain ways. A single water molecule isn't wet. Or life itself, it emerges from complex interactions of non-living molecules. Consciousness and thought are very often considered prime candidates for being emergent properties of the incredibly complex biological neural network that is the human brain.
So, the idea is that the subjective experience of consciousness, the process of thinking and deliberation, somehow arises from the collective, coordinated activity of billions of relatively simple neurons, even if each individual neuron just follows basic physical and chemical laws. The whole system, the brain, produces something mind-thought that seems like more than just the sum of its individual neuronal parts.
That's the core idea of emergence applied to consciousness. It might be a high-level property that arises from, but isn't easily reducible to, the low-level neuronal firings.
Okay, so if we tentatively accept thought as this high-level emergent property, could that emergent consciousness or thought process then somehow play a fundamental active role back in the physical universe? Specifically, could it be the thing that actually causes wave function collapse when a quantum measurement occurs?
Now, you're touching directly on a specific, rather historical, and highly speculative interpretation of quantum mechanics known as the von Neumann-Wigner interpretation. This interpretation, championed by physicists like John von Neumann and Eugene Wigner at different times, proposed something quite radical.
What did it propose?
It proposed that the wave function of a quantum system, which describes all its possibilities, doesn't definitively collapse into a single actual outcome until it interacts with or is observed by a conscious mind.
Wow. So the physical world stays in a fuzzy state of possibilities until a mind looks at it.
That's the essence of this particular interpretation. It gives consciousness a unique and privileged role in the physical measurement process. It suggests that consciousness is somehow the necessary boundary between the weird, probabilistic quantum realm and the definite classical world we experience. Your act of becoming consciously aware of the result of a quantum experiment is, in this view, what actually finalizes the outcome and makes it real.
So my thought isn't just reflecting reality, it's potentially creating it, at least in terms of resolving quantum possibilities.
That's the provocative idea embedded in the von Neumann-Wigner interpretation. However, it's really crucial to emphasize, as the source material notes, that this interpretation is highly controversial and is considered a minority view within the physics community today.
Why is it so controversial?
Several reasons. First, it completely lacks empirical support. There's absolutely no experimental evidence to suggest that consciousness, specifically, plays this unique role in wave function collapse. Experiments seem consistent with collapse, or the appearance of collapse via decoherence, happening due to interactions with any sufficiently complex measuring device or environment, whether a conscious observer is involved or not. Second, it's often criticized for introducing a subjective element consciousness, which we don't fully understand physically, into the fundamental, supposedly objective framework of physics. It raises more questions than it answers, like what counts as conscious enough to cause collapse? A cat, an ant, a thermostat.
Where do you draw the line?
Exactly. Most physicists today tend to favor interpretations of quantum mechanics, where collapse, or the effective appearance of collapse, is explained by objective physical processes like decoherence, the interaction of the quantum system with its macroscopic environment, which happens regardless of whether a conscious mind ever becomes aware of the outcome.
Okay, so the idea of thought as an emergent property that has this special power to cause quantum collapse is a fascinating philosophical possibility, historically discussed, but it's highly speculative and not supported by current scientific consensus or evidence.
That's a fair summary of its status.
So let's turn to the other side of the dilemma you posed. What if the opposite is true? What if thoughts themselves are not the cause of collapse, but are simply a deterministic property that arises as a result of external observation and the subsequent purely physical processing of that information within the brain?
This brings us right back full circle to the challenge of determinism, but now focus squarely on our internal mental world. If our thoughts, decisions, and subjective experiences are simply the fully determined outcome of physical processes.
Like light hitting our retina, causing electrical signals which travel to the brain, get processed through complex neural networks according to physical laws, which might include quantum laws at the micro level, but these effectively average out to classical behavior at the macro level relevant for thought.
Then it seems inescapable that our mental life is just as determined as the rest of the physical world. In this picture, free will, in the strong sense of being able to genuinely choose differently, still seems incompatible. Our thoughts and choices would just be the inevitable result of the inputs we receive and the deterministic, or perhaps effectively deterministic, machinery of our brains processing those inputs.
Which sounds very much like hard determinism. Again, the view that determinism, whether purely classical or classical emerging from averaged out quantum effects, is true, and therefore free will, in the sense of having genuinely open alternative possibilities, must be false. Our thoughts are determined by the external world interacting with our internal physical structure.
Yes. In this view, thought isn't an active agent causing things in the quantum world. It's more like a passive output of the deterministic physical world acting on our brains.
So the core paradox or dilemma that you've identified really highlights a profound tension. It seems we're caught between two difficult positions. One, if thought is an emergent property with the power to influence the physical world, like causing quantum collapse, that idea is currently highly speculative, lacks evidence, and faces major philosophical problems. Two, if thought is simply a deterministic or effectively deterministic outcome of physical processes happening in the brain in response to the external world, then free will, in the strong sense, seems to be an illusion, just a property determined by physics beyond our ultimate control.
Exactly. It beautifully encapsulates the fundamental and currently unresolved philosophical challenges that lie at the intersection of consciousness, physics, and free will. It shows just how deeply intertwined these questions are. What is the fundamental nature of physical reality? What are the rules governing it? How do complex systems like brains arise and behave according to those rules? And what is the nature of our own minds, our subjective experience, and our feeling of agency within that physical reality?
It really feels like trying to carve out a space for the kind of free will we intuitively feel we possess forces us into some very uncomfortable territory. We seem to be navigating between a universe where everything is rigidly predetermined and a universe where key events are merely random coin flips, and neither of those seems to easily accommodate our sense of being rational, conscious authors of our own choices.
That is a very accurate and eloquent description of the philosophical dilemma that has plagued thinkers for centuries, and which modern physics has only sharpened, not resolved.
Which naturally pushes us, as you did in your sources, towards considering potentially even more abstract, perhaps even more speculative concepts in search of a different perspective. This brings us to our final section, Section 8, extending the discussion to emergence, higher dimensions, and the holographic idea. You put forward a fascinating, though explicitly tentative, suggestion. Perhaps wanting to avoid answers for free will that are purely metaphysical or supernatural, you propose that conscious action, maybe even free will itself, could be understood as an emergent effect happening not just within our brain, but perhaps at a higher dimensional level of reality. You use the analogy of our familiar four-dimensional physical spacetime possibly being itself an emergent holographic projection of a deeper, more fundamental higher dimensional space. And you very honestly stated, I am at the edge of my understanding here, which, frankly, I think most people would agree with when exploring these kinds of mind-bending ideas.
Yes, this is definitely where we venture furthest into the realm of cutting-edge theoretical physics and philosophical speculation, moving well beyond what is currently testable or empirically verified. But it's a fascinating direction to explore precisely because it attempts to connect some very modern, albeit abstract scientific ideas to these ancient and persistent philosophical questions about free will and consciousness. You started from a premise that seems scientifically reasonable, that all action, including conscious action, must ultimately be a result of physical interaction, a broadly materialist or physicalist viewpoint.
Right. Assuming free will isn't just magic, it has to be grounded in physics somehow, even if it's physics we don't fully grasp yet.
Exactly. And you correctly brought up the concept of emergence again. As we've already discussed, emergence is a perfectly valid and widely accepted scientific concept. Complex systems absolutely can exhibit novel properties, like the transition from gas to liquid, the phenomenon of life, perhaps consciousness itself, that aren't obviously present in or easily predicted from their individual fundamental components. So it's entirely plausible, even within standard physics, that consciousness is an emergent property of neural networks operating within our familiar four-dimensional spacetime, 3 space plus 1 time, simply arising from the sheer complexity of the biological system, without needing to invoke extra dimensions at all.
Okay, so emergence itself is a powerful concept we can apply even within our current understanding of 4D physics. But you then took the extra step of connecting emergence specifically to the idea of higher dimensions and holography.
Yes, drawing inspiration from some of the more speculative but mathematically rich ideas coming out of modern theoretical physics, particularly the quest for a theory of quantum gravity. You mentioned the holographic principle.
Which sounds like something straight out of science fiction. What's the basic idea behind the holographic principle in physics?
The core idea, and this is simplifying it greatly, is a conjecture that arises in certain theoretical frameworks, most notably in string theory and the study of black hole thermodynamics, and especially in something called the AD-SCFT correspondence. It suggests, counterintuitively, that all the information needed to describe a volume of space, like a region of our 3D space evolving in time, making it 4D spacetime, might actually be fully encoded on a lower dimensional boundary surrounding that volume.
Like all the information about what's inside a room being somehow written on its walls.
That's the analogy. It suggests that a physical theory describing gravity and everything else happening within a certain volume of spacetime could be mathematically equivalent to a different physical theory, one without gravity, living entirely on the lower dimensional boundary of that region. The analogy is indeed like a conventional hologram, where a seemingly three-dimensional image is completely encoded in the interference patterns on a two-dimensional photographic plate. In some of these theoretical models, our entire 4D spacetime universe could be viewed as an emergent holographic projection of a more fundamental reality taking place on a distant boundary surface with fewer dimensions.
So our everyday reality, the 3 dimensions of space we move through, plus time, could, in some deep theoretical sense, be like a complex illusion or projection generated by physics happening in a different, perhaps lower dimensional reality.
That's the mind-bending implication suggested by the holographic principle, at least within the specific mathematical context where it arises. Now, it's crucial to understand, as the source notes, that this principle, even if true in some form, doesn't directly or automatically imply that consciousness resides in higher dimensions, or that free will operates from some higher dimensional control room. The holographic principle is primarily a statement about the structure of spacetime, the nature of gravity, and the fundamental limits on information density in quantum gravity theories.
Okay, so it's more about the physics of information and space-time geometry than about the mind directly.
Correct. However, what it does do is open the door conceptually to thinking about reality in fundamentally different ways. It suggests that reality might have different descriptive levels, that locality might not be as fundamental as we think, and that a complete description might involve considering these higher dimensional bulk spaces or lower dimensional boundary theories. It allows for, even encourages, thinking about non-local or holistic descriptions of reality.
And that's where your speculative leap comes in, connecting this possibility of different dimensional descriptions to the emergence of consciousness and free will.
Exactly. This is where you took the holographic analogy and applied it quite creatively to the philosophical problem. The speculative idea is something like this. What if consciousness itself doesn't just emerge from neural complexity within our 4D spacetime, but instead, what if it emerges from or is fundamentally linked to these potentially more fundamental, perhaps higher dimensional structures that underlie our perceived reality? Maybe it's connected to the dynamics of space-time geometry at that deeper level, as some very, very speculative ideas in quantum consciousness or quantum gravity sometimes hint at.
Okay, and if that were the case?
Then the speculation continues. Maybe the property we experience as free will could arise from the dynamics operating within those more fundamental, possibly higher dimensional structures. And maybe those dynamics operate according to rules that are not strictly local or deterministic in the way we understand those concepts within our perceived 4D classical or even standard quantum mechanical framework. Perhaps there's room for a different kind of causation or agency at that deeper level.
That is quite a conceptual journey. From a simple ball and a simple dome, we've somehow ended up contemplating consciousness emerging from the fundamental geometry of higher dimensional spacetime.
It is indeed a significant leap.
Mm.
And it's absolutely vital to reiterate, as the source material emphasizes, that this line of thinking, while intellectually stimulating and drawing parallels with concepts from modern theoretical physics, is highly speculative. It currently lacks any empirical support. There's no scientific evidence right now to suggest that consciousness operates from higher dimensions or that free will arises from holographic projections. It would require a revolutionary shift not just in fundamental physics, but also in our understanding of biology, neuroscience, and the very nature of the mind.
So the holographic principle provides a fascinating theoretical framework that allows us to mathematically and conceptually think about reality and perhaps even consciousness in terms of emergence from potentially different dimensional levels. And it certainly doesn't prove that's how reality actually works, or that free will originates from some higher dimensional source.
Precisely. It provides a new kind of mathematical and conceptual language that physicists are using to explore the structure of reality at its deepest levels.
Yeah.
And if consciousness were somehow intimately tied to those levels, which is a huge if, then this language might offer a new perspective on the age-old free will problem. It allows for the possibility of reframing free will not as some mysterious exception or loophole within 4D physics, but perhaps as a natural property that emerges from a deeper, more fundamental, possibly higher dimensional description of reality itself.
It's interesting. Viewed this way, this speculative idea could almost be seen as aligning with a very sophisticated, perhaps cosmic or dimensional form of compatibilism. Free will isn't breaking the laws of our 4D projection. Instead, it's understood as a higher-level description of complex behavior that emerges from the underlying, perhaps higher dimensional dynamics of fundamental reality, even if those underlying dynamics also follow their own deterministic or maybe probabilistic laws.
That's one way to interpret it, yes. It could be seen as a kind of multi-level compatibilism.
Mm-hmm.
Or, alternatively, if one were to speculate even further, perhaps the dynamics of those hypothesized higher dimensions themselves allow for genuine, non-random choice-like processes that are not captured by our current 4D physics. In that case, maybe that emergent self arising from the higher dimension could somehow influence the lower dimensional projection, our world, in ways that genuinely challenge 4D determinism.
Which, as you say, circles right back in a way to that paradox of the observer in quantum mechanics that you raised earlier, the idea of the observer influencing the system, but now scaled up to a potentially cosmic level involving the fundamental structure of reality and consciousness itself.
It does have that resonance, exploring the potential for mind or agency to interact with physical reality at fundamental levels, albeit in a highly abstract and speculative context.
So it feels entirely fair to conclude, as you did, that with these kinds of ideas, we are undeniably standing right at the very edge of current scientific and philosophical understanding.
Absolutely. These are truly frontier questions. They represent active areas of theoretical research in physics, intense philosophical debate, and profound mystery in neuroscience and consciousness studies. Science simply does not have definitive, empirically grounded answers right now on the fundamental nature of free will, on exactly how consciousness fully arises from physical processes, or on the physical reality and potential role of higher dimensions beyond their appearance in theoretical frameworks like string theory or the holographic principle.
But the analogy you drew, connecting emergence and holography to the enduring question of free will, serves as a really powerful illustration. It shows how modern physics, even in its most abstract and speculative forms, continues to provide new mathematical frameworks and conceptual tools that allow us to explore and perhaps reframe the deepest questions about the structure of reality and our own place within it.
It definitely shows the power of abstract concepts and theoretical models to push our thinking into new territories, even if, or perhaps especially when, they lead us into highly speculative zones that are currently beyond the reach of direct empirical verification. It's part of how science probes the boundaries of the known.
And with that exploration of the very boundaries of known physics and philosophy, that brings our incredible journey all the way from a simple mathematical dome to the potential higher dimensions of consciousness to a close for today.
It's quite amazing, isn't it? We started with what seemed like a fairly contained, albeit quirky, thought experiment about a ball on a uniquely shaped dome, a puzzle designed purely to probe the theoretical limits of classical determinism.
And we ended up grappling with the most fundamental aspects of reality itself. The nature and existence of determinism versus indeterminism, the enduring enigma of free will, the profound mystery of consciousness, and even venturing into highly speculative ideas about the very dimensions we might inhabit.
We saw how Norton's dome presents a fascinating classical paradox, a theoretical challenge to the universality of strict classical determinism, but one that arises from specific unphysical mathematical idealizations, rather than indicating a flaw in how Newtonian physics describes the real world in practice.
We explored why quantum mechanics, despite introducing its own inherent brand of indeterminism, doesn't really provide a straightforward resolution to the classical paradox posed by the dome, and why the dome isn't seen as a real-world scenario that necessitates bringing in quantum physics or unifying classical and quantum theories for its explanation.
We then carefully compared the dome to real physical equilibrium systems, like Lagrange points in gravity. We highlighted that crucial difference between a mathematical loophole potentially causing non-unique future solutions in a purely theoretical model, the dome, and the separate issue of ambiguity in reconstructing the past from an equilibrium state, like a Lagrange point, due to the nature of inverse problems and the potential loss of historical information.
And finally, we took the leap, connecting these intricate discussions about determinism and indeterminism directly to the profound and deeply personal question of free will. We touched upon the mind-body problem, the quantum measurement problem, and followed your insightful thread into exploring speculative but thought-provoking ideas about consciousness and agency, perhaps being linked to emergence and potentially even higher dimensions of reality, drawing inspiration from cutting-edge physics concepts like the holographic principle to help us frame these incredibly complex relationships.
And throughout this journey, it became clear that these are not settled issues. They represent some of the biggest, most challenging, and actively debated questions across physics, philosophy, and neuroscience. The sources you brought together offer various angles, different perspectives, and critical insights, but they also underscored that there's no single, simple, universally accepted answer to many of these questions. At least, not yet.
And that really is the beauty and I think the excitement of a deep dive like this one, isn't it? You start with one specific, maybe even technical sounding idea that sparked your curiosity. You follow the threads from your sources, guided by your insightful questions.
And suddenly you find yourself exploring these vast, interconnected landscapes of inquiry that touch upon the very foundations of physical reality, the nature of mathematical description, and the deepest mysteries of our own minds and our place within the cosmos.
It truly shows how that spark of pure intellectual curiosity, starting with wondering about a theoretical ball on a theoretical hill, can ultimately lead us to contemplate the fundamental fabric of space-time and the enduring enigma of our own apparent freedom to choose.
It certainly does, a testament to the power of asking why and what if.
So as we wrap up this incredibly expansive deep dive, we want to leave you, our listener, with a final provocative thought, something distilled from the rich material we've explored today for you to ponder on your own time. Here it is. Considering the challenges posed to simple determinism by both the theoretical edge cases within classical mechanics, like Norton's dome, and the inherent probabilities within quantum mechanics, and then considering the even more speculative ideas about emergence, consciousness, and perhaps even higher dimensions, where do you, in your own thinking, tentatively draw the line between the seemingly rigid laws of physics and our profound subjective experience of freedom? And perhaps just as importantly, how much of our understanding of reality and the very problems we perceive within it might be fundamentally shaped, maybe even limited, by the specific mathematical models and conceptual frameworks we currently choose or are able to use to describe it.
Those are some powerful questions to sit with indeed.
Definitely something to think about. Thank you for joining us on this deep dive.